Hey guys, welcome back to Algo's Explain. My name is David Kim, and today I'm going to bring you a question from LeetCode. And just for starters, the echo in this room is pretty loud. I usually have a lapel mic, but for some reason it hasn't been working pretty well. Like midway through my last recording, it started cutting off, and all you hear is white noise, and so that's why I can't rely on it. This is a medium level question on LeetCode, and it might go very long. Just a warning, it involves recursion, so I didn't want to record 30 minutes or something of video and have it be wasted. And so today's question we'll always link the question in the description, so check it out if you want. Maybe we could even go through it together. Or you could go through it as I'm explaining it here, but it is number 39, combination sum. And yeah, it's a medium level question. I usually don't do any of recursion stuff just because it takes a long time, and the attention span on YouTube is very, very much shorter than that, or whatever recursion can explain. However, I'm also going to paste my solution in the description, and so you can look at it from there, or you can go to the discussion on LeetCode and type in Algo's Explain or something, and then I'll have a post on there too, which just links this video. So you can do whatever you want. Okay, let's read the question. Given a set of candidate numbers, candidates without duplicates, and a target number, target, find all unique combinations in candidates where the candidate numbers sums to target. The same repeated number may be chosen from candidates unlimited number of times. Okay, and then note, all numbers, including target, must be positive integers. That's great. The solution must not contain duplicate combinations. Okay, so let's break this down. All this candidate talk it's a hard word to say, I don't know. It's just saying nums. That's all you have. Your input is nums. And what is it? Let's see. Without duplicates, the target number, you want to sum it to the target number without duplicates. Or they're saying in the input, there's not going to be duplicate numbers. And honestly, that doesn't matter if you're using my method. I actually started solving for duplicate numbers because I thought that was an edge case that I had to take care of, but it apparently it's not, now that I look at it again. But they're saying, okay, you have a set of numbers, some combination of this needs to equal the target number, and don't duplicate your answers. And so pretty much, if you have an input like this, and you have 7 and a 2, 2, 3, don't be giving us 3, 2, 2, or something like that. 2, 2, 3, 3, 2, 2, or any other form, because ultimately you're using the same numbers. And like this, 2, 3, 3, don't use 3, 3, 2, 3, 5, don't be giving us 5, 3. And that is important. We're going to address that later. Of course, we're going to address that in our algorithm. And they say also that the same repeated number may be chosen from the nums unlimited number of times. Looking at this one, 2, 2, 2, 2 equaling 8. So there's only 1, 2 here, but apparently we can use them multiple times. And if there was a 4 in here, we probably could use 4, 4. We could use 2, 2, and 4, something like that, because you can use these multiple numbers of times. And so those are just some of the regulations they put on us. I don't know, blocks, rules. But ultimately, let's look at what they want from us. They want, in terms of structure, they want an array of answers. And the answers themselves are going to be inside arrays. And so for them to want these to be unique, especially in JavaScript, is a little bit hard. Well, not hard using the method that I came up with later, but initially when I looked at this problem, I thought, okay, they don't want uniques. One method of excluding uniques, especially when you're working with graph problems, is to have a set of numbers that are represented in string format. And so I thought, okay, maybe I'll have the number and their index as some set. And I could just check the set, did I use this exact number at its index already, and if I did, then I wouldn't add it into this ultimate answer. And if I did, then if I didn't, then I would. If I did, then I would not. You get it. But that mapping thing it wasn't the solution that I came up with. one thing that this might sound similar to is the knapsack problem. If you know that, that is a recursive problem where ultimately you're like a thief, and the input they give you is just like this. It's an array of numbers, and it kind of represents the weight of each item, and the target is kind of the ultimate weight that you can carry away. And what they want to know, in that problem, what they want to know is they give you the weight and they also give you the value, and so it's a little bit more complicated, but they say what is the max value you can take away while not going over your weight, of course, because you want to take it away. And so this problem is very similar to that, whereas although we have to equal the target exactly, it's kind of the same idea. Is we take away the 2 and say, okay, can we put the 3 in there? Can we which ones can we use after that? And so that is kind of how I decided, okay, let me try to do this recursively versus iteratively through like some kind of for loop going through each and every single one of them. Okay, let me draw you a diagram of kind of how that recursive thought came upon in my mind, and maybe it'll make sense for you too. And so we know we have 8, and so let's have a question mark here, and we have 8. And so from this 8, pretty much when you're thinking, okay, a set of numbers need to equal a sum, the same thing you can do is take the number and work backwards. So subtract a number from the sum. That is just another strategy of doing things. And so we haven't taken anything away from here, so our potential is this guy. That is the number that we can take away from 8. And I'm using this one because it's just a cleaner example and it uses all the numbers. This one never uses the 6, so we'll go over this one, and then I didn't tell you, we're going to go over this. You probably already know, we're going to go over this. We're going to go over the solution and then maybe walk through another one of the examples. If this video isn't going to get too long, although warning, it might. So we have an 8 here, and pretty much what can we use to take away from this? Well, we can, if we use the 2, then what we're left with is a 6. If we use the 3, what we're left with is a 5. If we use the 5, what we're left with is a 3. And so that is kind of the number we're going to use. And the bottom one is how much the new target is. And so, okay, just like that, like, doesn't that look a lot like kind of what we started here? 2 and 6. If we use another 2, because we're allowed to use the same number unlimited amount of times, the next problem we have to solve for is filling up this target of 4. At this 3, if we were to have used the 2, then we have to worry about taking care of a target of 3 more. And say from this, if we use the 2, we have to worry about using or taking care of a target of 1. And so let's build out this branch fully. If the new target is 4, and if we were to use a 2, then we have to, our new target is 2. And if we were to use 2 again, our new target is 0. And so that's kind of how you know, okay, this was the perfect branch. This branch is perfect. It ended up at a 0. If we were to have used anything else, say, if we were to use a 3 here, that'd be a -1. If we were to use a 5 here, that would be, -3. And so ultimately, those are not what we want. And so in our equation somewhere, we're probably going to check, okay, if it's a 0, we'll do one thing. Well, of course, if it's a 0, we're going to celebrate, do one thing. If it's negative, then we're just going to fail it. And we really don't know if we're going to fail a branch until we get to the very end, or until we get to one of these cases. Because once we get negative, we know for sure, okay, there's really no point in moving forward. But if we're at a 2, then we won't really know, should we use the 3 or the 5, especially if we're at a 1. We don't know, okay, is there more we can do? Because every time we're here, we're not going to iterate through the array. That would be a waste of loops. And so even from here, we branched out to all 3. From here, we could branch out to all 3 too, right? If we were to use a 3, we would have a 1 left. If we were to use a 5, we would have a -1 left. And so, of course, at the 3, we could branch out to the 2, 3, and 5 again, but that would be negative. We already know that's going to be a dead case. And once we're already negative, it's a dead case. And so For these two, I'm just going to ignore it because we know, although in the algorithm will go through more branches at this point still because it hasn't hit a base case yet. And at the 6, it's going to go through a 3. We're going to have a 3 left. It's going to do a 5. We're going to have a 5 left. This one is going to go through a 3 left and then 0. Success case. This branch is perfect, just like that branch. Let me circle this. And at this case, we're going to do more also here. What is it? Or here, we can do another 3 again, which is a 0. That is a success case. And although this is technically not the solution that we came up with because it's going to repeat numbers, but we're going to go over that in just a second. This one can use a 5, and that would be a 0. That's a success case. This guy can use a 3. That would be a success case. All right. I know there are a couple of branches that I haven't hit, but then this is enough. We certainly have everything that we do need already. Let me check recording real quick. Okay, good. All right, just have to check on the recording. So, success case, we know that there's a 2 here, so if we just look at all the branches that we branched off of, we know that this one ultimately gives us this. That's one of our answers here. And this one right here, this one is a 2, 3, and a 3. That was that branch, so 2, 3, and a 3. But if we look at this one, this is a 3, 2, and a 3. 3, 2, and a 3. And this one was a 3 and a 5. 3 and a 5. And this one was a 5 and a 3. 5 and a 3. And so this is kind of exactly what my first run of this question was. By branching out like this, I only thought to branch out like this because, well, we needed to sum up to an 8, and so why not subtract down from an 8? That would be a lot easier than trying to kind of, I guess another method someone might have been attempting was take the 2, add it to the 3, and then add it to, or make some kind of like constant comparison of each and every single number, but you can subtract it down. I feel like that's a lot better. And once I started branching out like this, I thought, okay, well, we haven't used a number yet, so we can use this, this, and this. We already know that. That's like the choices that we have, because from 8 we can go to a 2, we can go to a 3, we can go to a 5, because at this stage we have the full set of numbers at our disposal. And then once I looked at this, 2 and a 6, well, now it seems like I'm doing the exact same thing, but pretending the target is a 6. That's all I'm pretending. I'm pretending the target is a 6, and I'm working with a 2. And so now, and then I just completed the branch, and so I ended up here. And by the time I was already here, and I kind of recognized, okay, it looks like we have a new target, but while we have a new target and we have a number that we have established, it seems as if we're doing the same exact thing. And so that got me thinking, okay, this is probably a recursive problem, or I could at least use a recursive solution to solve this. And so once we branched out all the way here, I started making all these calculations too. I still went to the 3, I went to the 5. Once I got to here, we could go to the 3, we can go to the 5. Well, that's kind of useless. These were all dead cases. From the 2, 6, check this out. We went to the 3 and we went to the 3. We also went to the 5, which there was no 5 left. From that point, there was 1 left, and this is a dead case. Okay, so we went to the 3 and a 3, and so that was another success case. And so we established that we have one answer here, we have another answer here. Okay, so now let's look at the 3 branch. Now the 3 branch goes out to say, okay, 3, 2, and 3, which is the same as this guy right up here. These guys are the same. And the only reason why we did that was because we didn't limit the 3. See how we are at the 3, but we're still using the 2. And so what I decided was, okay, what happened if, I mean, these don't have to be in numerical order, so don't waste your time sorting it. But once I'm at a later stage in the array, what if I limit this set of possible values to kind of where that number is by itself. And so if I were to branch to the 2, sure, I can use the full set. If I were to branch to the 3, maybe I should just be using the 3 and a 5. And once I branch to the 5, maybe I should only be using the 5. And if I were to follow this rule, you can see that how this would have never happened. This branch right here, this one uses a 2, yet there is no 2 available to me because of this rule I set on myself. And so this branch would have never happened, which means this duplicate would have never happened. Yet at the same time, it doesn't limit me from branching to a 5 here and creating this solution. Now, once we're at the 5, he still has the this one still has the freedom to, well, it has the freedom to do anything it wants, but really it only has the freedom to use another 5 and get to a -2, because it never had the 3, and so it can't go through this route. And it definitely can't go to the 2. It doesn't have the 2 available to it. It only has the 5, and if it were to do a 5, it'd be a -2, and it'd be caught by the base case. And I'm starting to say things like base case because, again, I decided this is going to be, I'm going to create a recursive answer for this. And in a recursive algorithm, you always need a base case and kind of a way to, well, I guess the most important thing is the base case, or else your recursion is going to go on forever. And then you need a proper way of bubbling up and saving the data. Or not saving the data, but passing the data back up. And so I think that is a good enough example. Let's go ahead and take a look at the algorithm.